In the beginning of this video series, this hour, we talked about the word and as being represented by multiplying, and we haven't actually used that yet. We're going to start taking a look at that now. And now we're going to be in the context of what it's a different kind of probability a little bit. It's called theoretical probability because when we work with things like tools of chance, like cards and dice and roulette wheels and whatnot, these are the kinds of problems that you can solve just by thinking about it, essentially because each outcome is equally likely. So it's in these kinds of problems that the word and especially comes up as being multiplying. Here's the first example. We're going to draw a card and roll a die, and we want to find the probability that both of them are 5. Now, first of all, I want to talk about the importance of rewording probability questions. Probability questions are asked in the English language, which is very complicated and non-standardized. There are 100 different ways to ask a probability question in English, but we only know how to solve a few of them. We really only understand how to solve probability questions if they use the words and or not. If they use different words like both or at least one or things like that, we have to do the job of rewording the question. So instead of saying both are 5, how could you reword that using the words and or not? Well, for example, you could say if both of them are a 5, that means that the card is a 5 and the die is a 5. So now we get our chance to turn and into multiplying. So we're going to interpret that as being the probability that a card is 5 times the probability that the die is 5. If you pick a card from the deck, there are 52 cards in the deck, and 4 of them are 5s because there's a 5 of hearts, diamonds, clubs, and spades. So the probability of choosing a card to be a 5 is 4 out of 52, which reduces to 1 out of 13. Times, when you roll a die, there are 6 values on the die, and only one of them is a 5. So I hope you didn't think that this probability would be 5 out of 6. Just because this is literally a 5, it doesn't mean that there are 5 5s. There's only one 5. So the answer to this problem would work out to be 1/13 times 1/6 as a fraction 1 over 78. Now the AND rule, just like the OR rule, has a simple version and a complicated version. We just looked at the simple version with the card and the die, and we were able to just multiply their probabilities together. It gets a little bit more complicated when one of those selections affects the other one. And the most common example of that would be like drawing cards without replacing. So in other words, if you take a deck of cards, and we are going to choose one of them, and then we're not going to put it back in the deck. We're going to keep it out. And then we are going to select another card. Okay. So now we've chosen 2 cards, and I kept the first card out before I picked the second one, selecting without replacement. So let's see how that would affect the probability formula. Again, the probability that both of them are 5, we want to reword that using the word and. That means the probability that the first card is a 5 and the second card is a 5. We want the probability of all that to occur, so the parentheses doesn't close till the very end. So again, we can, in fact, break this down as 2 separate probabilities. that are multiplying. But we're just going to have to think a little bit more carefully about how this process affects that. So the probability that the first card is a 5, as we discussed before, is 4 out of 52. Because there are 4 5s out of 52 cards. However, now that I have picked a card out of the deck, and assuming that it's a 5, of course, how many cards are left in the deck? There are no longer 52, but there are now only 51. Furthermore, how many 5s are still in the deck? There used to be 4, but now one of them is out here. I just picked one. So how many are left in here? There are 3 left. Therefore, the probability that the next card would be a 5 would be 3 out of 51. The deck has changed because that first 5 was already chosen. Right? Remember that if we're going to consider this process to be successful, it means the first card has to be a 5, and so does the second one. So when we were counting the deck the second time, we were assuming that a 5 had already been chosen in order to be successful. So we end up with the pattern of what's called descending integers. 4 times 3, 52 times 51. And that pattern is going to keep coming up quite a bit today. And that is always associated with this process of not repeating something or not replacing.